Hi everybody, and welcome to the second lecture of 6838. I'm glad everybody returned to at least one more class. Today we're going to begin our technical discussion, not by really talking about geometry so much, but rather doing a quick review of linear algebra and calculus, which are essentially tools that we're going to need throughout the entire semester. Now, I don't know if my goal intentionally today is to confuse you or not, but we're probably going to use notation and constructions that are a little bit unfamiliar from your undergrad linear algebra class, and that's okay. So if this goes by kind of quickly, what I would suggest to our students is to spend some time, since this class is online anyway, you can watch it at half speed, or you can go through the course notes that come with this lecture to make sure that you get every detail, because I think a lot of the notions we'll use today you might have seen, but they might have blown past in 5 minutes of your undergrad linear algebra class. That might be a couple years old. You might not be used to thinking about this stuff. So it's worth reviewing. Incidentally, as a person who also authored a numerical analysis textbook, I can't help but introduce a few general ideas that we might not need in this course, but I kind of feel like just as grown-ups in computer science, you all should know. So here's our basic motivation for today. One of many perspectives, obviously this is extremely debatable, is that you can understand linear algebra as some version of geometry that only applies to flat spaces, right? We spend so much time in linear algebra class talking about essentially just planes, hyperplanes, and affine spaces that don't have curvature, but they're still geometric objects, and a lot of the calculations we can do on those spaces can be viewed through a geometric lens. So in part one of today's lecture, we're going to talk a little bit about how linear algebra fits into geometry and also just review some notions that you've probably already seen, but maybe you haven't seen in the notation that's common in the geometry community. Then, in the second part of our course, we're going to step back further and look at nonlinear problems through the lens of optimization. So we're going to first review some ideas from calculus class that you might have forgotten, things like essentially Lagrange multipliers and so on. And then at the very end of today's lecture, I'm not sure that we'll be able to squeeze it into the class period or not. If not, then you can watch it at home. We'll talk about variational calculus, which is not an idea that I will have expected you to have seen in the past. Variational calculus is how to do optimization when your variable is like a function or something rather than a point. So let's get started. First, we're going to talk about linear algebra, and we're also going to introduce some really terrible notation that geometry people like. If you're curious, historically, this terrible notation is Einstein's fault. So we can thank him for some math writing that we all have to do these days. So to get started, let's do a few preliminaries here. So in 6838, we're going to think of our vectors as column vectors, and I'm going to use bold letters to refer to these objects. Right? So bold X here is a vector. For matrices, we will use capital letters. And then this little T symbol here in the third row is denoting the transpose. So if we transpose a matrix, it's like, rotating it 90 degrees roughly, or flipping it 45, or, flipping it over its diagonal, I guess. We can also transpose a vector, and just by convention, we're going to think of a vector as a column matrix, like an n by 1. I guess the by 1 is implicit here. So the X transpose is 1 by n. So a little bit of shorthand that's useful to remember. Remember that X transpose Y is just fancy notation for a dot product. So let's think about that for a minute. So let's say that I have a vector X, and I'm going to write it as follows. So here's X. And I can think of the components of X as X1 through Xn. Okay? And similarly for Y. Okay, so then if we write X transpose Y, well, what is that going to look like? Well, if we think about it, X transpose takes our vector and flips it on its side, right? So this is going to look like X1 to Xn, and then Y1 to Yn, like that. Okay, and remember how dot products or matrix products work, right? I go kind of like this, right? Horizontally in the first term of the product, vertically in the second, right? So this is like x1, y1 plus x2, y2, dot, 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 plus xn, yn, which we can write like this. should be plus xn, yn, which of course is nothing more than the dot product between x and y. Now, those of you who have taken my 6837 class, my undergrad graphics class, might remember that we used all kinds of fancy notation to distinguish between vectors and affine spaces and base points and this and that. And this is a really useful notion for an undergrad graphics class where these kinds of things are a little more unfamiliar. But in 6838, we're all going to be adults here, and I'll probably get pretty sloppy with notating vectors versus matrices versus everything else in very similar terms. So if ever any of you guys are stuck, feel free to ask a question and we're happy to address it. Now through the magic of video here, I'm going to pause and erase the board, and then we'll continue. Okay, so now we're back in action here and all cleaned up. So for a little bit more notation here, we're going to notate the elements of our vectors as with superscripts here. So if a vector has components v1 through vn, I suppose I just violated that writing on the board a minute ago. We're going to write it as v superscript 1 to v superscript n. And we'll denote the standard basis using subscripts. So remember that like e sub 1 is the vector that's like 1, 0, dot, 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 0. e2 is 0, 1, 0, 0, 0, 0, and so on. It's just the standard basis vectors. So this is going to be our basic notation in 6838 for linear algebra. Now, as a little bit of review, now we've talked about vectors. Of course, the next object we should think about is a matrix in our linear algebra discussion. And I would argue that matrices show up in linear algebra class actually in two different places. And this is what I've shown you on the screen here. Now, obviously, these two things are related to one another, but we're going to see in our discussion of geometry that actually both of these are going to play really critical roles when we do mathematics in tangent spaces of manifolds and so on. So one place that we see a matrix is when we talk about linear operators. So if we have a linear operator from one space into another, meaning that it satisfies these two properties I've shown you on the screen here, then we can show that that operator, at least on a finite dimensional space, is given by a matrix. We'll derive that in just a moment. And then another place where we see matrices come up is in quadratic forms, like dot products. So for example, if I have a function g, which satisfies the four properties that I've shown on the screen, symmetry, that I can pull constants out, like g of au comma v is equal to a, g of u comma v, linearity, and then finally positivity, we'll see that we can also write g as an inner product. In fact, that positivity line is optional here. So let's see an example of that. This is basically just a little bit of linear algebra review. Remember that a linear functional is anything like our functional L, which satisfies these two properties. Incidentally, when I'm talking about a function itself, rather than a function evaluated at a particular point, one very common piece of notation is to put just like a little dot here, right? So this is saying that really our discussion is involving the function L rather than L of x at a specific point x. Okay, so just as a little bit of review, let's say that I have a functional L that satisfies these two properties that I've shown you on the screen highlighted in yellow. Then I'd like to show that in a finite dimensional space, L is actually given by the action of a matrix. So let's derive that. So here's how we can do that. Remember that in a finite dimensional linear space, I can take any vector and write it in the standard basis, right? So I can write any vector x as the sum over, say, k of x, k, e, k. So remember that this is the standard basis vector, right? And so this is kind of like a vector. If we wanted optionally, we could put this little symbol here. And then xk is the coefficient in front of it. So what happens if I apply our linear map to x? Well, let's do it real quick. So L of x, I can write x in our basis. So we have L of the sum over k, x, k, e, k, like that. I'm going to drop this vector sign because we're all grown-ups here. And now, by the properties that I've shown you in the upper corner here, I can pull out the scalar piece. I can pull out the sum, and what I get is that this is the sum over, oops, it's supposed to be a sum, over k of xk, this is a scalar, L of ek. Hopefully that looks familiar. And if you look really carefully, this is actually the definition of a matrix vector product. The question is, what is the matrix and what is the vector here? And actually, we can write it as follows. So I'm going to construct a matrix whose columns are these vectors, essentially L applied to each of the standard basis vectors. So the first column is L of E1. Maybe I put these vertical lines here to kind of remind us that this is a vector. L of E2, and so on, up to maybe L of En if I'm in n-dimensional space. And I can write a vector next to it, x1 to xn. And if we step back 10 feet, I'd do that here, but I'd hit onto the wall. What I would end up seeing is that these two expressions are equal to one another. So what did I just show? I showed that if I have any map L, which satisfies the properties that I've given you on the board here, then essentially that map L is determined by its action on the standard basis vectors by writing the matrix vector product that I've given you on the screen here. Okay, so in other words, anytime I have a linear map, necessarily I can think of that linear map as being given by a matrix vector product. Hopefully that makes some sense, and it's just a little bit of review from your linear algebra course. So let's erase that really quick. Okay, all gone. So similarly, let's say that I have a function of two vectors, g of u comma v. I claim that this also can be written as a function of just a bunch of constant evaluations at our standard basis functions. So in particular now, let's write the following, which is I can write my vector u is equal to a sum uk ek in our basis, sum over k. Similarly, I can write v is equal to a sum in our basis of v, maybe l, el, like that. So now let's evaluate our functional u, or g rather. So if I do that, then I have g of u v is equal to g of the sum over k, uk ek, and the sum over l, v, l, el. And now, by the axioms that I've laid out here, of course, I can pull out the sums and the constants. And what I get is that this is a sum over k and l of u, k, v, l, g of e, k, e, l, like that. And now, if I construct a matrix whose elements are these values here, then what I've essentially shown, if this is BKL, is that this is exactly U transpose B V. So again, what did we do here? Essentially, we started with a few axioms about a function that G kind of looks like a dot product, right? It's symmetric, it splits over sums, it's positive. We didn't actually use the positive property, by the way. And what we can show about G is that secretly it can be written as this quadratic form that I have on the right. So why did I go to all this work? Essentially, the point here is that matrices show up all over the place in linear algebra, and two of the really important places where they appear are when we talk about dot products, right, or inner products more generally, or even quadratic forms, and linear maps. These are two really critical applications of linear algebra that both are given by matrix vector products, or so it seems. All right. So essentially, these are two different derivations just to show the kind of calculations that we tend to do in linear algebra applied to geometry. And indeed, in order to make this kind of calculation a little bit less tedious, Einstein proposed some notation that is a giant headache, at least for me. In particular, there's a convention that we often have in geometry called Einstein Notation, where any time that we see an index twice, there's implicitly a sum over that index. So here, remember that our vector was the sum over k of vk times ek. But because there's an upper and a lower index with the same letter, here, the letter k, Einstein essentially proposed dropping that letter from our sum. Now, why did he propose that? Essentially, from Einstein's perspective, there's very, very rarely going to be a case where I don't have that pair and where they're not summed over one another. We're going to see that there's some really deep reasons for that geometrically, but I do think it's worth just being aware that this is a convention in geometry, that oftentimes we drop the sum over k here anytime that there's an index twice. So if you see like a really weird expression in differential geometry where it seems like you're missing a sum, that's because you probably are. Right. So to return to our discussion again, the point so far is that there's sort of one data structure here, a matrix, that we've used in two different ways. One of them is to encode linear maps. That's what we see on the top of the slide here. Remember that a linear map is one that satisfies those three properties that we gave before. The other one is that we can use matrices to encode inner products. Right? So one of these is a functional that takes in x and outputs a times x. The other one is kind of like a dot product, takes in u and v and outputs u transpose times bv. But these matrices a and b here, we show that these are byproducts of the properties of our functions, right? Specifically, we showed that any function L, which satisfies these two properties on the top, can be written as a times x, and any function g of u comma v can be written that satisfies the top three properties here, can be written as u transpose times b times v. Okay, so here's the thing. If I just give you a matrix, like I just give you a big table of numbers and I don't tell you what it's useful for, it's really difficult to, especially if your matrix is square, to distinguish between these two cases. That is to say that the matrix is actually not the interesting part of a linear algebra problem. It's what you use the matrix for. And a matrix that's being used for this first task of being a linear map isn't necessarily a useful matrix to define an inner product and vice versa. And so essentially, this Einstein notation and where we're going to place our indices is going to help us distinguish between these different types of matrices. So specifically, when we have a linear map, we're going to think of the elements of the matrix, like that matrix that we derived a few slides ago, as being indexed with one upper index and one lower index. Now, why do we do that? Well, remember that we're going to use upper indices to refer to the elements of a vector. So for example, on the right, after the first equal sign here, you see that there's a v superscript k. So what's going to end up happening? Well, remember that I can write a matrix vector product by going along rows of my matrix L. So here's what I can do. Well, I can write matrix vector notation by saying maybe I define a vector W as L times V, but I can also do some really slick notation with this Einstein setup by doing the following, which is that if L has elements, let's see here, K, J, like that, well, then one thing that I can do is I can say, okay, well, what is Wj? Well, let's see. We can take the Vk, Lkj, like that. Remember that implicitly here there's a sum over k because the k index is repeated twice. And one thing that you should convince yourself at home is that this kind of slick piece of notation here is nothing more than this matrix vector product that we're seeing on the slide. Okay, so similarly, if we have a quadratic form, we can essentially repeat the same proof that we wrote a few slides ago, but drop all of the sums out of our notation here. So here, if I have a quadratic form g of u comma v, I can write u and v in the standard basis. So for example, u is equal to, the coefficient uk times ek. And then this is implicitly summed over k because there's a repeated index. Similarly with v, I can write as vk ek. Then the proof on the screen here is exactly what we just walked through to show that there's a matrix sitting behind a quadratic form G that satisfies those properties, that they split over sums and so on. But this notation suggests something kind of interesting. In particular, as shown on the slide here, I can write g of u comma v is equal to a double sum where we have u, k, v, l, g, k, l, where this value is nothing more than g evaluated at e, k, e, l. Okay, so let's compare our two boxed equations here. Well, what do we notice? So here, the matrix of the linear map, I notated by having one upper index and one lower index. Here, the matrix of my inner product, I notated using two lower indices. Why is that? Well, I had an upper index k and an upper index l, and I kind of want to cancel those out and make a double sum. So this is the notation that kind of compiles. Okay, so what's going on in these two expressions? Essentially, both of these objects, g and l, represent matrices, right? They represent big tables of numbers, but one of them is being used as a quadratic form, and one of them is being used as a linear map. And the kind of beautiful thing about this upper and lower subscript notation is that I can distinguish between the two. So a different way to put that is that by using this fancy upper-lower index notation, I actually have some means of doing type checking. You know, if I were a computer scientist talking about a compiler, I would have a very similar setup. But essentially, if I have two upper indices and there's not a lower index that's kind of canceling it out by summation, then probably something has gone wrong in my derivation. And this was Einstein's clever observation. So again, to summarize, when we have linear maps, we're going to think of the elements of the corresponding matrix as having one upper index and one lower index. When we have a quadratic form, we're going to think of elements of the matrix as having two lower indices for now. And whenever we have a repeated index, like k and l, implicitly, we're going to think of our expression as summed over that repeated index. Now, in this class, I probably am going to avoid that last convention and just write out the sum a lot, because honestly, it makes me uncomfortable as a mathematician. But it is worth kind of knowing and getting used to this notation, because it shows up a lot in geometry. Okay, all gone. So anyway, that was our quick introduction to Einstein summation and this index notation where I can distinguish between linear maps and quadratic forms depending on where the indices are. Now, if you want a good challenge problem to think about at home, a good one to ponder here, I've given you an optimization problem on the left-hand side and a linear system of equations on the right-hand side. One thing that you can prove using Lagrange multipliers is that the minimizer of 1/2 x transpose ax minus x transpose b, the minimizer x necessarily has to satisfy ax equals b, at least if a is symmetric. And the question is, can you describe this pair of expressions in Einstein notation? This is a bit of a tricky thing to ponder, because in the optimization problem, a is being used like a quadratic form. And then on the right-hand side, a is being used like a matrix. So something happened here. And this is what's worth thinking about a little bit. Okay, so continuing to define some interesting and useful terminology here. So far, we've been talking about matrices and vectors. A lot of times, I'll be using the phrase linear operator. And this is the object that inputs a vector x and outputs a times x. So these are dual to one another. That's essentially what we just showed, that we can talk about matrices and vectors, or we can talk about linear maps or linear operators that input vectors and output vectors and satisfy those two properties. Okay, but this second notion of linear operator actually has a lot of interesting analogs in infinite dimensional spaces. So for example, let's say that I'm in the space C infinity. So this is the set of functions on the real numbers. And I look at the functional that gives me the second derivative. Now, what does that mean? Here, I'm thinking of L as a function that inputs a function and outputs another function. So for example, let's say that I have a function f of x, right? It's just the function x squared. Then L is kind of this weird meta object that doesn't operate on like points in Rn, but rather on functions, right? And it's going to output another function. So I can write this crazy notation, right? So this object here is a function because L is a linear map of functions. And in particular, it outputs the object which is the negative second derivative of something. We're going to see that this is a really important functional called the Laplacian later on in this course. So what is the second derivative of x squared? Well, it's just actually identically equal to 2. Okay, so this abstract example is really critical, and in fact, we can still talk about eigenvectors and so on. So you probably remember from your linear algebra class that an eigenvector of a matrix is one that satisfies ax equals lambda x for some scalar lambda. And we can actually talk about eigenfunctions of linear maps. So in particular, one thing to kind of just place into your mind and think about for later, let's say that I have a function f of x equals cosine of ax. Okay, so what is minus the second derivative of f? Well, it's, if you work through it, what you're going to get is a squared cosine of ax. Right? The second derivative of cosine is going to be minus cosine, but there's a minus here. And I get an h coming out by the chain rule each time. Okay, so what does that mean? Well, this is a squared f of x. So in other words, what did I just show? I showed that cosine of ax is sort of an eigenfunction of the operator that takes in f and outputs minus the second derivative of f. So what is this operator? It's something that takes in a function and outputs another function, right? This is kind of like our replacement for a matrix, but we're still able to compute things like eigenvectors, which is a pretty crazy construction if you're not used to it. That went by a little bit quickly, that's okay. In a couple lectures when we talk about the Laplacian, we're going to do this calculation in much more detail. But this is just to say that the reason that we talk about functionals and so on is that some notions from linear algebra, like eigenvector, are still applicable even though we're in some infinite dimensional space. So in this case, our space is C infinity of the real numbers, which is like the space of infinitely differentiable functions of real numbers. Okay. Okay, so in any event, let's get back to reality and talk about some more concrete problems. So at the end of the day, when you took your linear algebra class, you no doubt solved a lot of systems of equations that looked like what I show you on the slide here. Essentially solving ax equals b, where your input is a and b, and the thing you're trying to solve for is x. Right, in undergrad linear algebra class, we have a bad habit of having our undergrads do Gaussian elimination a million times for no real reason. The good news is that as grown-ups, we don't actually have to solve this by hand, and there are many great algorithms for doing that. It's a little bit outside of the scope of 6838 to talk about different algorithms for solving linear systems of equations, but essentially we're going to assume that as a black box, a lot of times there's software that given a matrix A and a vector B can solve this linear system assuming that A is invertible. So the most common strategy for doing that is something called Gaussian elimination, which is essentially just an algorithmic version of the steps you probably were used to writing down in undergrad linear algebra class. There's one thing that I am going to underscore with all of you today, however, which is that solving ax equals b is not the same thing as computing A inverse as a matrix and then multiplying it by b. There are a lot of algorithms that can solve ax equals b given a and b and just give you x as output that are more efficient than inverting a and then multiplying. And in fact, sort of a basic tenet of numerical linear algebra is that you should never compute A inverse explicitly if you can avoid it. So if you find yourself doing that on your assignments, something probably went wrong. There's probably a linear system of equations you could have set up. And so I would encourage you to go back in your code and fix that. I would encourage you that because otherwise you probably won't get full credit on your assignment. However, actually, I'm going to point you guys toward one kind of interesting paper that appeared on Archive a few years back that actually argues that that matrix vector product is maybe nearly as accurate as solving a linear system directly. the accuracy actually isn't always the concern, but rather efficiency and not making use of structure in your matrix A. So one of the cool things that happens a lot in our geometry processing discipline is that our matrices are extremely structured. Now, what does that mean exactly? Well, oftentimes when we solve problems computationally, we set up some matrix A, we set up B, and we solve AX equals B, we can leverage special structure that we know about the matrix A to solve it more quickly than normal. So for example, let's say that I wanted to solve some version of this second order system of equations. So maybe I'm given a function g and I want to solve for a function f whose second derivative is g. Well, one thing I could do is approximate the second derivative on some grid and then solve a linear system to try and recover f from g. And if I do that, what I'll end up with is an extremely structured matrix. So let me grab my pen here. And we'll actually try and do that really quick. So in particular, let's say that I have a function f, and I just discretize it on the real line here. So I have a bunch of samples like f1, f2, and so on, and they're spaced distance h apart from one another. Well, then roughly I can approximate the second derivative d squared f dx squared. Well, this is the derivative of the first derivative, and I can approximate the derivative at the midpoints quite simply. So in general, if I have f k and fk plus 1, then I can think of some version of the derivative sitting here that looks like fk plus 1 minus fk divided by h. Okay, this is some simple approximation of the derivative that I might think of as sitting in between my two samples. So then an approximate second derivative kind of looks like the following if I evaluate it at some point k on my grid. Then it looks like a fk plus 1 minus fk divided by h minus fk minus fk minus 1 divided by h, all of that divided by h. Right? So this is some approximation of the second derivative. And if I do a bit of algebra, this is nothing more than 1 over h squared of fk plus 1 minus 2 fk plus fk minus 1. So if I wanted to solve the system here, I show on the slide, right? So in other words, my input here are a bunch of samples from some function. So maybe g1 through gn. And what I want to output is f1 through fn such that the second derivative, dx squared, is roughly equal to g. Then one simple way that I could discretize this as a linear system of equations is to say, okay, well, roughly this object here should equal gk. And if I write that as a linear system, I get what's shown on the slide on the right-hand side. Notice here that I'm going to think of values of f beyond the end of my grid as just 0. Okay? So if I do that, then I can factor as a matrix here. I'll let you convince yourself of this at home. And the point of this exercise is not necessarily to just tell you how to solve the second order system of equations, but rather actually to just look at the matrix that I'm giving you on the slide and observe a bit of structure in this matrix. So in particular, there are all kinds of things that we can say about it. Most of our matrix is 0. Hopefully you see that only 3 bands of values, right down the diagonal and then the one off diagonal, actually have non-zero values inside of this matrix. And everything else is just absent. So there are a lot of things that we can say about this matrix. It's actually sparse. We can say that it's actually negative definite. That's not clear from the way that I've written this matrix, but you can convince yourself of that at home if you like. And so many times the algorithms that we have for solving these linear systems of equation can do better than the general case. So in particular, we already talked about how you never want to construct A inverse explicitly. This is a great example where that's certainly the case. In particular, this matrix is sparse, but if you type it into MATLAB and you compute its inverse, you'll see that the inverse is actually a dense matrix. So whereas this takes order n memory to store our matrix, we'll see that the inverse of this matrix takes order n squared, which is no good. But also it turns out that there's special linear system solvers out there that can take advantage of sparsity, symmetry, positive definiteness, bandedness to solve your linear system of equations even more efficiently than normal. So some of the classes of linear solvers that are worth reading a little bit on Google. Again, it's outside of the scope of our class to really go into detail here. I'm just giving you search terms for later. Include direct solvers. These are basically extensions of Gaussian elimination that directly try to recover the solution of ax equals b. And also iterative solvers that are kind of closer to gradient descent and iteratively get better and better approximations to our linear system. So in this course, we're going to think of essentially having a black box piece of software that can solve linear system of equation, and we're not going to worry ourselves too much with what goes on inside of the algorithm, except that if your matrix is sparse, you should leverage that property as much as possible. And the reason that sparsity is going to come up so much is that in this class, one of the structures we really care about is the triangle mesh, like what I show you on the slide here. And many of the matrices that we're going to construct essentially have one row per vertex in our triangle mesh. And the only non-zero entries of our matrices are going to have to do with the edges in the mesh. And so that's a fabulous example where most of our matrix is actually just a bunch of zeros. And making one giant dense matrix would be a lot of overkill. So in 6838, there's no need to implement a linear solver. There are many built in the slide here. I have some pointers through the Julia and MATLAB implementation. And if you have a sparse matrix, you should store it as a sparse matrix on your computer, and your homework is going to give you a lot of practice there. Okay. So what we've done so far in our linear algebra review is shown that linear maps are given by matrices, so are quadratic forms. We've shown that those matrices are often quite structured and that there exist nice solvers for solving those systems of equations. We're going to think of those solvers like black boxes in this class when we do our homework and implementations. Okay. So returning to our outline for today, the first half of our talk was to get a little bit of notation and summary of linear algebra, specifically maybe to introduce this idea of Einstein notation and placing your indices carefully when we talk about linear algebra, which is probably a new idea relative to what you may have seen in your math courses. Now let's review a few ideas from optimization, and then we're going to wrap up by introducing variational calculus, which is a little bit tricky. Okay, so that's our part 2 here. As an aside, one thing that I would encourage you all to review is something called matrix calculus. So oftentimes when we think about calculus, like minimizing a function f of x with respect to x, we think of x as a vector. There are actually many problems where your unknown in an optimization problem isn't a vector, but is actually a matrix. And so differentiating functions with respect to matrices is super valuable and useful. This is an idea that shows up all over the place in machine learning, for example. So if you're not used to it, I would encourage you to look at 2 things. One is this nice little thing called the Matrix Cookbook, which has all kinds of useful formulas in it. And another thing that's really fun to play with is probably the #1 link on my browser is a website called matrixcalculus.org, which is essentially a piece of software that can compute a lot of matrix derivatives that you might not want to do by hand. So I encourage you to pause this video and play with that website just a little bit to get a feel for the kind of calculations that we're going to do. So in optimization, there's a little bit of terminology that's worth reviewing. Remember that when we optimize, essentially we're trying to minimize some function, maybe f of x. And we usually use 2 different terms to talk about the thing we're trying to minimize. Sometimes we'll call it the objective function. Sometimes we'll call it an energy function. And these are just exchangeable terms that are worth knowing. And then oftentimes what we do is we say that we're going to add constraints to our optimization problem, right? Maybe I'm going to maximize profit for my company subject to not using up all of the materials I have on hand, right? So that ST, that subject to, is enforcing constraints. And they typically fall into 2 categories. They're equality constraints and inequality constraints. And both of these are going to show up in many of the problems that we'll solve in this course. Now, in calculus class, when you're supposed to optimize something, compute the minimum of a function, what do? Well, typically you take the derivative and you set it equal to 0. But now we have functions possibly of multiple variables, so the first thing we have to do is talk about what it means to differentiate something. So we're going to introduce one notion in today's lecture, which we're going to use throughout this course, and this is called a differential. This is one way to motivate how to compute the partial derivative of a function, but we're going to see that it generalizes really nicely to curved spaces. So here's the basic idea. If I'm trying to do calculus with some function that operates on a space that's bigger than one-dimensional, then I have a lot of different directions where I could take a derivative, right? So for instance, if I have some region in the plane, and I have some function f that operates on this thing, so maybe f takes a region on the plane and then maps it to the real numbers here, meaning that at every point in the plane I get a different value for f. So let's say that I'm sitting at some point x here. Now, one thing that I can do is try and take ideas that I had in one variable calculus and make them work in higher dimensions. So one way that I could do that would be to say, at a point x, I'm going to draw a vector v. Okay? Now, I can define an object called the differential, which is what I show you on the slide here. Where what am I going to do? I'm going to start at x, move some distance h along v to another point here, and basically compute a divided difference and take the limit as this goes to 0, right? That's exactly what's going on in the definition on the slide here. So in some sense, we can think of df as a directional derivative, meaning that I'm essentially taking the derivative of f at x in the v direction. Okay, so why is this terminology useful? Well, for one, it motivates a formula that we all know and love from calculus class. So in particular, let's say that I write out a Taylor series for my function f, right? So in particular, I'm going to write a Taylor series for f centered at x0, right? So I might do this. Well, what is this? The 0th order term is just f of x0. And one thing I could do is sort of take the Taylor series of f as a function in one dimension along its first variable, and then along its second, and so on. And what I'm going to end up finding is that this is equal to the sum over maybe index k of h, where I take the partial derivative of f in the xk direction, evaluated at x0, plus some higher order term. Okay, so why did I do that? Well, if I take this expression, I subtract off this, and I divide out by h, right? That's exactly what I do in the definition of the differential here on the slide. And I take the limit as h goes to 0, what I'm going to find is that df at x0 in the v direction, well, let's copy our definition. This is the limit as h goes to 0 of f of x0 plus hv minus f of x0 divided by h, right? Which is, hopefully you see, is kind of like differentiating our function just in the v direction. But now if I plug in this expression here, what's going to happen? Well, I'm going to subtract off this f of x0. So I'm going to get limit as h goes to 0. And I'm dividing by h, so I'm going to have, oh, oops, and I needed to times a vk here, sorry. And so I'll get that this is the sum over k of df dxk, evaluated at x0, by the way, scaled by vk, plus big O of h, right? Because this thing got divided by an h. And what is this expression? Well, here, these are the elements of the gradient of f. Remember that the gradient of a function is nothing more than the vector of all of its partial derivatives. So, and this term vanishes as h goes to 0. So what we're left with is the gradient of f evaluated at x naught dot product with v. And that's the expression that we show you on the slide here. So what did I just do? I defined a function. This is a really complicated way to do something you're probably used to from linear algebra, but is really, really important. So this object is the one to think about a lot. So df at x0 is itself a function of v. If that sentence didn't parse, you should pause and think about it for a minute and try again. The df at x0 is a function of v. And in fact, it's a linear function. And it's given by this expression down here. And what is this function trying to evaluate? It's the directional derivative of a function f in the v direction at point x naught. Now, these are all pieces that you're probably used to from calculus class. You've computed lots of gradients, maybe even directional derivatives. It's just important to see how all of these different notational pieces fit together, because of course when we do optimization problems, all we're really doing is, we talk about setting the gradient equal to 0. Equivalently, we can think of setting the differential operator equal to 0, and we're going to see that that's a really useful perspective. In fact, we're going to return to that at the end of today's lecture. Okay, so there's the basic object that we wanted to define, which is the differential of a function. And we see that when we define the differential, we essentially just end up with the gradient, which is probably the familiar object that you've computed in calculus class any number of times. So continuing in our discussion here, let's just review a few terms from calculus class. So remember that the gradient of a function is just the vector of its partial derivatives. This is something you can probably compute in your sleep. And the Hessian of a function, the Jacobian of a function is the matrix of its partial derivatives when our function inputs a point in Rn and outputs a point in Rm. Right? So the gradient is specifically for scalar functions. Jacobian is a slightly more general notion where it includes functions from one space into another. This is like a matrix of partial derivatives. And finally, the Hessian of a scalar function is the matrix of second derivatives. And you'll probably recall that the Hessian is a symmetric matrix, and it can be used to make a second-order Taylor series of a function, like what I show you on the bottom of the slide here. So if we want to do optimization, if we have an unconstrained problem, of course, all that we're really doing is searching for points where the gradient equals 0. But if we want to be really picky, that's actually an insufficient criterion, right? It's necessary but not sufficient. Because, of course, there are many different types of points that have the gradient equal to 0, right? There are minima, maxima, and saddle points. So these objects are called critical points. But the high-level idea is that, in general, when we solve an optimization problem by setting its gradient equal to 0, somehow what we're doing is converting an optimization problem into a root-finding problem, which is a pretty useful idea and one that shows up a lot. Now, optimization encapsulates many different types of problem. For example, let's say I want to solve the linear system ax equals b. I could actually write that as an optimization problem by minimizing the residual, or the norm, of ax minus b. Right? So there's this duality. I can either solve the linear system of equations ax equals b, or I could minimize this functional on the first line here by taking f to be the norm of ax minus b. Similarly, if I want to find eigenvectors like ax equals lambda x, you can actually convince yourself at home that if you choose this specific f and g on the slide here, then x will necessarily be the smallest eigenvector. And even if I just want to find roots, like the zeros of function g, I can do that by just getting rid of the objective function, setting f equal to 0, but I still have to find an x that satisfies the constraint. So this is an incredibly general problem, the way that I've written it in green. Well, if we step back and ask ourselves a very simple question, which is, how effective are generic optimization tools? What do you think the answer is? Like, if I give you a piece of software and I tell you, you give me an f and a g, and I'll give you the minimum of f of x with respect to x subject to g equals 0. I don't care what the form is of f and g, just give me your functions and your gradients. Well, that piece of software probably isn't going to work terribly well, right? Because this includes linear system of equations, eigenvalue problems, traveling salesman problem, all kinds of NP hard things. generic optimization tools are really not going to be effective. And so what that means is that, just generically speaking, a good idea is to try the simplest algorithm first. So what does that mean? That means we look for structure in our optimization problems, and we try to leverage it to solve our problem as efficiently or as easily as possible. So for example, let's say that I have an optimization problem of the form that I've shown you on the board here. So I want to minimize 1/2 x transpose ax minus b transpose x plus c, subject to a linear constraint. Well, what can I do? I mean, I could put, the objective and the constraints into some generic solver in MATLAB and just see what happens, but it turns out that I can do much better than that. In fact, just as an exercise, let's work out precisely what that would be. So here's what we can do. Remember that we now have a constrained problem, so what you need to do is introduce Lagrange multipliers. So here, our Lagrangian is a function of our unknown x, and our Lagrange multiplier, maybe we call that, I don't know, lambda. Lambda is actually a vector here because we have a vector constraint, and it looks like the following. It's 1/2 x transpose ax minus b transpose x plus c. And remember how the Lagrangian works? I take all of my equality constraints and I just scale them by the Lagrange multiplier. So here I'm going to have lambda transpose times mx minus v, like that. Okay. And how do I solve constrained optimization problems? Well, I take the Lagrangian, I differentiate it with respect to x and lambda, and then I get my first order optimality conditions. So for instance, if I differentiate with respect to x, my Lagrange multiplier here, what am I going to get? Well, I go to matrixcalculus.org and I type in my expression, which everybody should do. You should pause this video and give that a try. And what you'll end up with, if I can do this off the top of my head while lecturing in this extremely unnatural environment, we're going to get ax minus b. This is a constant, and then we'll get plus m transpose lambda, like that. And similarly, if we differentiate with respect to lambda, our Lagrangian here, one thing you might know is that that just gives you the constraint, so that's mx minus v. So combining these two expressions here, what do we get? Well, I can put x and v into a vector. If I look at the first one, I'm going to have ax, and then we have an m transpose, oh, oops, that should be a lambda here, sorry, that's my unknown, not v. I'm going to have m transpose lambda. Down here I have mx, I don't have a lambda. And now I have all the constants, so I'll move the b to the other side and the v to the other side, like that. So what did I do? I started with an optimization problem, what's shown on the corner of the slide here, and I derived an equivalent linear system of equations. So was it necessary for me to solve my optimization problem using some fancy generic nonlinear solver? No, I can just solve this linear system of equations and get exactly the same result, probably much more efficiently and in a numerically stable fashion. So if we summarize in nice mathematical writing here, we have the following equivalence, which is that this optimization problem on the top of the slide is equivalent to the linear system of equations I've given you on the bottom. And in fact, there are many different special cases here that are worth noting. So for example, if I want to solve this least squares system here, we'll see that that's equivalent to the normal equations at the bottom of the slide here, which I'll let you review at home here. Okay. Okay, so let's do a quick applied example of this from some of the literature here. So one sort of basic optimization problem that we often encounter in geometry is embedding or parametrization. So here we have a 3D face and we want to map it into the plane. One way that I can do that is to look at the positions of all of the vertices of my 3D mesh in the plane as variables of an optimization problem. So if I want to write that problem out, one simple model for doing that, which we'll cover again later in this course, just to give you an idea of where these kinds of linear systems appear, looks like what I've shown you on the slide here, where essentially xi, xj are positions of different vertices on my triangle mesh. And so what this optimization is saying is if two vertices are adjacent on my mesh, I'd like the position that they end up in the plane to be nearby. Right? And this is a good parameterization property, right? If I look at the triangles here, I want I don't want them to be like long and stretched out and flipped over. I just want them to be nearby. So this is a quadratic objective, and I've got some constraints. Namely, I'm going to take all the vertices on the outside of the face here and just prescribe their positions. That's a linear constraint. And this actually, just if we follow the proof that I just did on the board here, is going to give me a very famous parameterization algorithm called the Tut embedding, which we're going to cover later in this course. Or if we choose a weighting for these different spring terms, then we'll end up with something called the harmonic embedding. Now, one thing that I need in order to make the Tut parameterization work is to prescribe the positions of the vertices around the outside of this disk-shaped model. So if I don't do that, what's going to end up happening? Well, now the best way to make xi and xj close to each other is to just make them all the same point, right? Which wouldn't be a very useful parameterization. So the boundary constraints are really useful and important here. If v naught, like the set of vertices that I just pin, is the empty set, then I get a useless map of my triangle mesh into the plane. One way to get around that might be to make all of the vertices square sum to 1. And that's actually going to lead to an eigenvalue problem, which is something that I'll let you convince yourselves of at home. And in fact, just adding that constraint leads to a very well-known technique called spectral conformal parameterization. That went by a little quickly. That's okay. That's not our point here. Of course, not all optimization problems end up being linear system equation. If so, our machine learning colleagues would be kind of out of business. But many of them do end up being unconstrained optimization problems, where maybe I'm trying to minimize some function f of x, where f is basically unstructured. So there are many algorithms that we can use for solving this sort of a problem. For instance, one that's probably pretty well known to all of you is to use gradient descent, where I have some estimate of the minimizer x, and I can improve it by walking along the gradient of my function f by some small amount. There's also a technique called the Newton's method, which solves some quadratic approximation of my objective at every single point and does that iteratively. And by working with less constrained versions of my function f, I'm now open to a much wider class of problems that I can try and solve. So for example, one problem that can fit into this domain would be shape interpolation. So let's say that I have as input the elephant in a few different poses, and I want to animate the elephant moving from one pose to another. One way that I might do that is to make my variables the positions of the elephant in the intermediate frames of my animation. And I could solve an optimization problem that has all kinds of crazy terms. Like, for instance, I have that I want the edge lengths to kind of interpolate linearly from one pose to another, or maybe the dihedral angles or the interior angles of my triangle mesh. Now, these are nonlinear functions of vertex positions, so when I write out this whole problem, basically I'll just get one giant unconstrained optimization problem to solve. Now, in today's lecture, I'm not going through the details of these papers, just kind of give you an idea of the sorts of problems we can solve with these different pieces of machinery. There are all kinds of software tools out there for solving unconstrained problems. In MATLAB, fmin-unc is a well-known technique. The BFGS algorithm is a good one. And indeed, that's one that you can try quite easily. That just needs a function, its gradient, and optionally its Hessian. In practice, we just try a bunch and see which one works the best for our particular problem. So finally, in our whirlwind review of optimization machinery, let's talk about constraint problems. In particular, we're going to review something you probably saw in calculus class and forgot, which is Lagrange multiplier. So Lagrange multipliers are useful for problems with equality constraints, like what I've shown you in green on the slide here. Right? So I want to minimize some function f of x, subject to the constraint g of x equals 0. So what I'm attempting to show you on this slide is some pictorial version of that optimization problem. So here, I'm going to think of these different curves as level sets. So x is some point in the plane. And so the concentric circles here are trying to essentially show you that f gets smaller as I move inward toward that center point. The circles are level sets. But I have a constraint, which says that I can't just choose any x in the plane. I have to choose an x for which g of x equals 0. That's the red curve that I'm showing you on the slide here. So Lagrange multiplier is trying to give us some analog of take the gradient and set it equal to 0 in the presence of this equality constraint that I have to deal with. So here's the kind of pictorial way that I like to motivate what's going on with Lagrange multiplier. Remember when we talk about gradient ascent and gradient descent, the basic point is that the gradient of a function is pointing uphill for that function. So I can draw the gradients of f and g as follows. So in fact, I'm going to put a minus in front of the gradient of f because I want to solve a min problem. So minus the gradient of f is kind of pointing inward from the concentric circles, right? So if I'm standing at this gray point here and I walk along the gradient direction, that's going to be the direction that decreases f, right? That's the gradient descent algorithm. But now I'm going to write a second vector, which is the gradient of g. And here's the kind of funny thing. Whereas I want to minimize a function f, I need to prescribe that g equals 0. I want to move along a level set of g. Well, take a look at that gradient direction. Can I move in the g gradient direction? No, I have to move orthogonally to it, because that is the way that I can walk without affecting the value of g. So in general, if I'm at a suboptimal point of my optimization problem, essentially what's going on is that there's some component of the gradient of f that I can walk in that's orthogonal to the gradient of g. But when I'm at the minimum of my constrained problem, then the gradient of f and the gradient of g are parallel. Why is that? Well, one way to think about it, remember the gradient of f is the direction that I walk in to make f smaller or bigger. The gradient of g is the direction that I walk in to change the value of g. So if these two vectors are parallel, what it's saying intuitively is the only way to make f smaller is to violate my constraint. Right? That's really what's going on with Lagrange multipliers. And another way of putting it is that the gradient of f is parallel to the gradient of g. And so, of course, I can write that as this condition here, that grad f is equal to lambda grad g. And this is known as the Lagrange multiplier condition for a constrained optimization problem. Now for inequality constraints, there's something called the KKT conditions. We're not going to talk about those in today's lecture, but they're worth a Google search if you're not used to this kind of calculation. So working with constrained optimization problems can give you all kinds of interesting things. So for example, let's say that I choose f to be the quadratic form, x transpose ax. I choose g to be the norm. Well, then if I optimize, for example, x transpose ax subject to the norm of x equals 1, then just plugging in to this Lagrange multiplier condition at the bottom of the slide here, I'll actually find that ax equals lambda x when a is symmetric. And that's exactly the eigenvector problem that we've already talked about. So again, Lagrange multipliers are essentially converting our constrained optimization problem into unconstrained root finding problems by introducing an additional variable lambda. And that's going to be a very useful thing. So again, just like we take gradient and set it equal to 0 all the time in calculus, now we can do the same if we have an equality constraint. There are all kinds of fun problems that we can solve here. So for example, if you have a reliable tool for solving equality constrained optimization, I'll refer you guys to this fun paper that takes curved triangle meshes and converts them into polycubes, which are essentially surfaces that are piecewise flat. This is useful for meshing and other tasks. Here, the optimization objective is trying to make sure that your surface doesn't distort too much and that its vectors, its normals, are aligned to the x, y, z coordinate direction. And it has a constraint that the surface area of the output surface looks like the surface area of the input surface. So I'll let you read that paper for more detail if you like this kind of thing. So with that, we've concluded our kind of review of algebra. This is also my practice for using this board technology here. So if our lecture is a bit all over the place, that's okay, and I promise it's going to improve. So I'm going to pause here and just make sure that we really understand the key concepts. The key concepts here are to remember what defines a linear map and a quadratic form. Those are those properties that I showed you at the beginning of the lecture. To understand the Einstein summation convention, where if I see an upper index and a lower index, I'm going to sum over it, even if I didn't write the sigma explicitly. And this notation also allows us to distinguish between quadratic forms and linear maps based on where we put our indices. Then we had a quick discussion of different types of optimization problems. And we did define one new object, which was the differential, which is basically a fancy function that computes directional derivatives at some fixed point x naught. And we found that really secretly this thing was just encoding the gradient of a function. So in the remaining time that we have in today's lecture, I'm going to introduce a new idea. And this is an advanced idea. And the reason I'm going to introduce it now is that I think it's hard. And so I want to introduce it today. It's going to be on your homework. It's going to be on the homework after that. We're going to keep practicing with this because I think it's one of these calculations that's really useful and one that we're not used to seeing from undergrad calculus class. And so I'm going to introduce it now, and I want you to really think about it a lot at home. And that is an idea of variational calculus. Now, we're not going to prove a bunch of theorems of variational calculus. We're just going to introduce the high-level ideas from this domain. And the basic idea, and one that's really critical for geometry, is that many times in optimization, our variables or our unknowns are not numbers or vectors or matrices, but they're shapes or functions. Right? So like maybe I want to make a function that is as smooth as possible, or I want to find a shape that minimizes surface area. These sound like optimization problems, but the problem is that my variable is like a shape. Right? So it's not clear what it means to take the gradient and set it equal to 0 anymore. And so the idea of variational calculus is to try and use machinery from calculus to solve these extremely abstract optimization problems. And this is going to leverage all of the intuition and ideas that we've developed in this course so far. So the basic construction, I'm going to warn you, this is like crazy notation ahead in about t minus 20 seconds, is going to be an object called the Gateau derivative of a function. And the first time you see it, it feels like really yucky notation. Looks like this. So here, I'm going to have an object which is a functional cursive f here. Now, a functional, we're going to think of as an object that inputs a function, doesn't input a scalar or a vector, and it outputs a number. And our job is to optimize that functional in the space of all functions. Now, I know this is a lot to digest, and so this is something we're going to return to and practice a lot this semester. I'm just going to introduce the idea today. So the question is, can we come up with some analog of a directional derivative that works for functionals? And that's what the Gateau derivative is. So remember, we already introduced an object called df, which is the differential of a function f. Now, if I have a functional, I can introduce the differential of my functional evaluated at a particular function. Woof! I know this is hard to digest. So that's the notation that I'm showing you on the right-hand side. And we're going to see is that it's extremely close to what we've already done. So let's put our slide in the corner here and do a little bit of writing. So in particular, let's take the definition of the Gateau derivative and expand it a tiny bit. So by the way, sometimes we put the u in a subscript, right? So we might write df evaluated at u of psi, like that, which is a little bit closer to the notation that we saw in our earlier slides for the differential. So our definition here is that this is equal to the derivative dh of f evaluated at u plus h psi, and then we take h to be 0. One thing that we can do is expand this derivative as a limit, and what we'll find is that it looks awfully familiar. So it's the limit as h goes to 0 of our functional f evaluated at u plus h lambda minus our functional f evaluated at u, all divided by h, which is basically exactly the same as our derivative, our differential functional that we derived earlier in today's lecture for finite functions. So this is really crazy operator that's trying to differentiate a function of functions in a directional derivative. Now, why is that going to make sense? So for example, maybe on your homework, we'll have you prove something really simple, like the shortest path between 2 points is a line. So in other words, I want to minimize length subject to my curve going through 2 different points. So then my functional here would be length And the different curves would be functions of t with the constraint that they go through those two locations. So let's do a really famous example here and derive something called the Poisson equation. Again, this is an advanced topic and one I do not expect you to get on the first try, but I want you to return to this construction a few times through this course and see if we can get it by the end of the semester. So here is a great example of a variational calculus problem. So let's see if we can unpack this notation a little bit and then derive the underlying partial differential equation. So the basic idea is that, let's say that we're in some domain. So maybe my domain is some region, some region omega. There it is. And as input to our problem, we're given a vector field v of x. So what does that mean? That means that at every point x, so here's x, in case you're wondering, there's some direction attached to x that we're going to call v of x, right? As we go to different locations, maybe v points in different directions, but it's just some vector field. So this is the input to our optimization problem, and our output is some function f of x. So our unknown in our optimization problem is a function, but we want this function to have a particular property. So maybe the property that we want is that the gradient of f is aligned to our vector field at each point x inside of omega. Now, the first question you might ask is, can I make this squiggly equal sign a true equal sign? And the answer is no. So for example, if I have a vector field that points in a circle, then it's quite easy to convince yourself that there never can exist a function f of x whose gradient is v. If you remember from physics, this is the difference between a conservative vector field and a non-conservative vector field. So let's say that this is our optimization problem. And essentially our task in our last 30 minutes of class here is to derive some notion of taking the gradient and making it equal to 0. So here's going to be our basic construction in variational calculus, is that we're going to suppose that f is optimal, and then we're going to try and take some directional derivative of our functional, which is this thing shown in the upper right corner here on the slide. So what does that look like? So here, I'm going to have a functional, capital F, which inputs little f and wants to ask how well aligned the gradient of f is to this input vector field v. So one way that I could do that is maybe take the integral over my domain omega and just subtract the two. So I have, v of x minus the gradient of f at x, and take the squared 2 norm and integrate that over my area. So what is this saying? This is saying that I'm going to look at the difference between my vector field and the gradient of f, and when these things are perfectly aligned, this functional is equal to 0, and when they're not aligned, that functional becomes a larger value. So hopefully now we can see how this is starting to look like optimization language that we're used to, right? We're trying to minimize over all functions f the agreement between the gradient of our function and the input vector field. This is a theoretical problem, right? I can't write a piece of software that solves this because these are infinite dimensional variables. So the question is, how can we convert this into a tractable finite problem? Well, here's one way to do it. So let's suppose, and I'm only going to do this informally. We're not going to do all the formal proof behind this, but suppose that f is optimal for our optimization problem. And moreover, take another function, g. Now, in reality, g is going to need to be differentiable, smooth maybe. We're going to need some properties on g, but we're not going to worry about it for today. And I'm going to define some new function. I'm going to call it p of h. And P of h is going to look like the following. I'm going to take my functional f, I'm going to evaluate it at my optimal f plus h times g. So notice that when h is equal to 0, then I get this thing. And when h increases, now I'm going to get some term involving g. In particular, just for fun, we can write it out. So this is going to be the integral over omega of v of x minus gradient f of x minus h gradient g of x. Oops. Okay. So why would I do that? Let's think about plotting our function for a minute. So here, let's say that I have a plot, and my horizontal axis is h, and my vertical axis is p of h, like this. So I have some value here, right, which is exactly this value that I've written on the slide. Here's the thing, can my function, so notice that whereas this is a function of functions, which is awfully complicated, p of h is just a function of h, right? This is just a thing that takes in a scalar h and outputs another scalar p of h, so I can plot it. But if f is optimal, can my function decrease? Well, no, right? Because f is the minimum possible value of my functional. So the only thing that this function of h can do is increase, at least locally, around h equals 0. This is something you should convince yourself at home, that, again, h equals 0 had better be a local minimum for this functional, oops, you can't see this on the screen, p of h, because essentially that's exactly the assumption that I made, is that f is the smallest possible value of our functional cursive f here. Well, here's something kind of useful. Whereas this is some weird, crazy object that's taking in functions and then mapping them to scalars, p is just a good old function that we know how to work with from calculus. So in particular, if this is a local minimum, well, then what do we know? We know that p prime of 0 is equal to 0, right? It's a local minimum. And so what we're going to do, say, aha! Now we have some analog of setting the gradient equal to 0. Incidentally, notice I didn't say anything about g. G could be anything. And that's what's kind of powerful here, that p is really parametrized by some function g, and that this expression is true for any choice of g. So let's actually expand what that tells us about life. Okay? Let's see if I can fit this on the board here. So what are we going to do? We want to compute p prime of 0. Well, what is that? That is exactly d over dh of our functional applied to f plus hg, evaluated at h equals 0. And this is, of course, the functional df, I guess, evaluated at f in the g direction. And we convince ourselves that this is equal to 0. And now let's actually do the calculation. Let's actually compute the Gaussian derivative. So, well, what do we need to do? Let's substitute this expression here. So we have d over dh of the integral over omega of v of x minus gradient f x minus h gradient g of x integrated over our domain, like that, evaluated at h equals 0. Whew. Now, this integral is over x, but our derivative is with respect to h. So we can actually interchange those two. Right? This is called differentiating under the integral, is the fancy term for it. Or just, if you think of the integral like a sum, the sum's over x's, it's not over h's. So these two things are kind of independent. So I can basically move this d over dh inside. Okay, so, oops, this should be squared. What happens when I do that? Well, now I go back to matrixcalculus.org, right? I mean, the fact that these are gradients don't really matter, right? They're just vectors, because the thing that I'm differentiating with respect to is h. So this is the integral of v of x minus gradient of f x minus h gradient of g at x. It's supposed to be an x. Dot producted with gradient of g of x. Now, why is that? This is just by the product rule. So this is one that you should convince yourself of at home. And it's basically just differentiating this expression with respect to h. And again, remember that we're substituting h equals 0. So this seems like an opportune moment to do that, because there's just one h term here. So this is the integral over omega of v of x minus gradient f of x dot product gradient g of x. Okay. So now we're cooking with gas. Now we have an interesting expression. And we're going to do one additional thing, which is to integrate by parts. I warned you, we're going to scrape up all those things from calculus class that you probably forgot. But by integration by parts, remember that can be written as a boundary integral minus something where I move the derivative to the other term. I encourage you to open up the Wikipedia page for multivariable integration by parts and review it. This is also called Stokes' theorem. And what do I get? I get that this is the, I'm struggling with this marker. This is the boundary integral over the boundary of omega, let's see, of g of x times v of x minus gradient f x dot the normal vector over the boundary minus the integral through the interior, where I take this gradient and I move it to the first term. So now I have the divergence of v of x minus gradient f of x dA. Okay. Whew. So where are we so far? We started at 0, and we ended up with this expression down here. Oops, with a g of x in front. Okay, so why did we go to all this work? Well, this is true for any function g of x, very weakly determined. So this is true for all choices of g that are suitably well behaved. So one thing that you can convince yourself is that, well, if this is true for all functions g, well, if we again draw our domain omega here, well, I could make a function g that's maybe peaked right at some point here, right? Or maybe I make another function g which is peaked at some other point over here. And regardless, when I do this integral downstairs, I have to get 0, even if like g is 0 on the boundary and just really sharp at some point x. So here is what you can convince yourself of at home. I'm going to switch markers. Hopefully this will work better. Is that essentially by these two terms having to equal 0 for any choice of function g, in particular in the interior of my domain, in the interior of omega, I must have that this expression equals 0. And why is that? Again, I can put any g I want in front of this expression, and I always get 0. So that means that, in particular, those two things, that second thing had better equal 0, right? It's kind of like, if I have a number and I multiply that number by any other number and I get 0, then that thing had better be 0. That's essentially exactly what happened here. So if I step back 50 feet and look at the proof that I just wrote, notice that I got rid of g here. I started with an optimization problem, right? We started here, and then what we ended up with is this, which is kind of like setting the gradient of our optimization problem equal to 0. So what we showed is that any f that is a local optimum of this optimization problem has to satisfy this partial differential equation, which is known as the Poisson equation. Now, why did we go through all of this derivation here? Essentially, the point here is to show that the objects that we've defined in class today, like the differential of a function, are going to be useful even for abstract problems. So we're going to use very similar reasoning to what we just used today to do things like finding minimal surfaces that minimize surface area with respect to geometry and so on. Now, if this derivation was really challenging or you didn't follow, that's actually expected. So what I would encourage you to do is to step through it at home and ask lots of questions on Piazza and so on until you follow. Essentially, we're using all kinds of yucky machinery that you probably don't remember. You know, we've got some linear algebra here. I integrated by parts and in a multidimensional way. There's some partial derivatives, divs and grads, and so on. So these are constructions that you might not be used to or might not have thought about for a very long time, and that's okay. So again, this is a derivation I want you to introduce today, and we're going to return to it many times in this course. If you want a really challenging exercise and one that will check your understanding here and make sure that you're like a ninja at variational calculus, I'm going to propose one more problem, and I'm going to put it on the board and give you a quick hint on how you might solve it. So as a challenge, I would encourage you, now that I've erased the screen, to basically reproduce this calculation like about 10 times until it's comfortable for you. And I guarantee you it's going to be hard the first 9. And then you'll get it. It's really not so bad, and you should ask me and your TA David lots and lots of questions until you follow. Then once you understand that one, if you really want to level up and be a variational calculus ninja, a challenge problem would be to solve a constrained problem like what I've given you on the screen here. And now you've got to figure out how to incorporate Lagrange multipliers into your problem. This is an advanced thing and not something that I expect you guys to be able to do for now. So in any event, today's lecture is a little bit all over the place, but it's just to establish some notational common ground and scare you with a little bit of mathematics. When we resume next time, we're going to dive right into differential geometry for the next 2 lectures by talking about curves. Curves are relatively easy to work with from a geometric perspective, and essentially they're going to be a great introduction to all of the different considerations that we have to make when we do geometric calculations, both in the calculus sense, like what I just showed you, as well as how we translate that to discrete domains, in this case just big chains of line segments. So with that, I will see you guys next time. Have a great weekend, and I'll talk to you soon.